current work on optimization of Chombo crunch, NISAP code for Knight's Landing, and some brief introduction to the code. So this code is developed to simulate subsurface flows. So these flows, so usually it's very high complex geometry and porous media geometry, and this figure shows a sample of shale, and this sample is about 100 microns of size. And Chombo crunch uses a Chombo library, adaptive mesh refinement library, with computational fluid dynamics algorithms, and also it uses crunch flow pieces for geochemistry. So this first set of equations, Navier-Stokes, well known incompressible Navier-Stokes equation, and second set of equations is this is a reaction, chemical reactions. So this is a legacy flat MPI code with about 0.6 million of source lines. So it's mainly C++ code with very complex data structures to represent this complex geometry of solid phase. And it uses adaptive mesh refinement to resolve solution in the domains of high gradients. And this is second order schemes, because the choice of second order schemes because of accuracy for such complex geometry. If you go to higher order, usually it's difficult to get accurate numerical methods for high geometry like fractal geometry. And it leads to low arithmetic intensity, and there are some performance limits due to this. And geometry is given from image data, and yeah, it was scalable on previous generation machines on like Titan or Edison or Hopper, up to full scale machine. And the main feature of Chombo crunch is embedded boundary method. This is a cut cell. In computational fluid dynamics world, it's known as embedded boundary method or cut cell Cartesian method. So we have, for example, if our complex geometry is just a sphere, solid phase, it's represented by sphere. So we have rectangular cells, and we have plane cuts by planes due to solid geometry, and we have three sets of cells: regular cells, which are filled only with fluid; irregular cells, which have both solid phase and fluid; and covered cells, only solid phase. And different index spaces used for regular cells and irregular cells. And irregular cells also, as you see, for example, on this little plot, so it can have different number of phases. So this makes embedded boundary approach different from unstructured mesh approaches. So it's not Cartesian method approach like finite difference, regular finite difference, or finite volume, and it's not unstructured mesh. It's something in the middle, and it introduced some challenges for my project. And so, like, tiling is difficult to implement. Possibilities for vectorization are quite limited. Memory access pattern, it's indirect memory access, and there are a lot of jumps when we compute derivatives in advection terms or viscous terms, or in Laplacian for elliptic solver. So it's a lot of jumps in memory. And this is a Hotspot pattern. So basically there are two steps: it's predictor and corrector step. Most of the time we spend on corrector step. And there is self-censured projection. This is one elliptic solve, and algebraic multigrid solver used from PHI library. Viscous advance, it's free Helmholtz solver for each component of velocity. And also it's PHI library is used for viscous advance. And Hotspot, like in very high level, it looks like that is spent about 40% in PCIMG solver and about the same time in Chombo, in different EB Chombo, embedded boundary Chombo routines, like computation of fluxes, redistribution of mass, some refinement, coarsening and refinement operators, and about 20 to 30% is MPI time. Most of time it's spent in MPI way tool. This is a gray part chart. Also highlights some, no, not all hotspots, but some hotspots. So the first the optimization step. This is not the most recent version of slides. Okay. The first optimization step was to reduce load imbalance. So I've tried different load balancing schemes which are available in Chombo library, and Chombo it's very broad library, and it has a few types of load balancers, and each load balancer works better for certain situations. And I played with this, and I found that it's possible to reduce MPI time. So and we got about 20 to 30% of runtime reduction both on Icelandic and XEON. And second optimization step was memory footprint reduction. And Chombo Crunch, it has a huge footprint, memory footprint. There are a lot of temporal variables to get conservative transport and conservative advection schemes. And I use Valgrind, and it shows detailed, massive tool from Valgrind. It shows detailed heap memory usage, and with the help of Valgrind and some Chombo developers, so we reduced the footprint about 3x, and now the typical workload on a node, it fits to empty CD-RAM memory. And yeah, this is like this two plot shows before and after optimization memory footprint over MPI rank. This was on 16 nodes of Haswell Core phase 1. And the current performance result on single node, KML node, so using the roofline model. So we see that so first red point, it shows when I run only on DDR. So I don't use high bandwidth memory. And second point, it's when I use MCD-RAM memory. And the ratio is just 1.5x. So in theory, ideally, this is memory bandwidth bound code, and ideally I should see about factor of 5 performance speed up. And when I check VTune, memory access mode of VTune, and I see that I don't saturate MCD-RAM bandwidth. It's still the question, so we're still exploring why it's. So in DDR mode, so I have about 80 gigabytes per second. This is close to 90 to peak. And in MCD-RAM mode, so I have only about 130, 150 gigabytes per second. So on this unsaturated bandwidth, it explains this factor of 1.5 instead of theoretical 5. And also another thing that there is still gap with roofline estimation. So it's about factor of 20 for MCD-RAM mode and about factor of 6 for DDR mode. And this point highlights the full application, full flow solver. So right now I'm working on different kernels, try to understand where I don't saturate bandwidth and why I have this gap in a roofline diagram. And also the work which has been already a few months I'm working on, it's implementation of shared memory in flat MPI code using OpenMP. And so OpenMP is implemented over boxes. So each processes have a few boxes, and I put a loop. I put threads over the loop of boxes. Let's say in this example, if one NP rank has 4 boxes, and I've read data iterator over boxes. And the first problem which we got, it was multiple race conditions. So it's a very high level of implementation of OpenMP in the code. There are about 10 nested functions which are called from let's say from average cell to phase function. And to fix race conditions, so we used mostly Intel Inspector tool, and finally we found all race conditions. This is a difficult task because they're not deterministic, and it took us a long time. And this is just one example how we fix race condition, put in OpenMP pragmas like atomic and criticals, Fred private reference counted pointers increment here. So, and yes, short summary on what was done and what's the next steps. So memory footprint reduction was about 3x, which allowed us to fit MCD-RAM memory on each node. And MPI plus OpenMP, finally we fixed race conditions. And however, algebraic multigrid solver from PETSI remains unthreaded, and short-term plan is to use 16 MPI ranks and plus 4 threads in Chombo, and just 16 MPI ranks for PETSI. And long-term plan is MPI communication endpoints to enable this parallelism in PETSI using threads. And the current performance has will still outperform Knight's Landing about 1.3x. And vectorization is just 5% speed up using AVX 512 instructions. And so I checked different cluster modes. There is no much deviation in cluster modes. So best results was for Quadrant and SNC4, about 3% just improvement compared to SNC2. And high bandwidth mode, so it will be decided later when we'll get enough runs on multi-node, because right now it's difficult to tell cache mode if it's gonna work and scale well on multi-node. And very brief, if I have like 1 minute on bars buffer, so about I/O, so we're exploring capabilities of bars buffer to accelerate I/O and in some complex in transit workflows. So this is just architecture, some very high level. So bars buffer nodes integrated with compute nodes in a high-speed network. And this is our main diagram how we use bars buffer. So it's an intermediate area for exchange files between different workflows components, like visualization by visit, and main simulation code. Also there is movie encoder. This is the simplest example how we can use bars buffer for in-transit visualization. And this is a SLARM script. So it allows, main advantage that it allows to keep traditional workflow, just few changes in bash script, and almost no changes in source code. And due to high bandwidth of non-volatile memory of bars buffer, so we got speed up in transit visualization and I/O time. So these results compared bars buffer performance and cluster for different I/O intensity. Like every time step, we saved plot files and made visualization on every time step, and 10 time steps every 100 time steps, and there are significant improvement for bars buffer. So if you have more questions on bars buffer work, so we can discuss it later, because I put these slides if somebody is interested, so we can discuss it. So thank you very much, and I hope I didn't take much time.
So I think we don't have any time for questions, so let's thank our speaker.
that's about it. Yeah, David. Yeah. So I'm doing this talk on behalf of the team. So you might have a question, which I might not be able to answer, but we have another developer, Giuseppe Serrati, sitting here. So hopefully you can actually answer the questions. So we have 10 minutes. So before we go in, so I would like to give a few remarks. So this is about reconstructing particle trajectories in high energy physics on XEON and XEON Phi. This is not taking the current existing code and porting it to XEON Phi architecture. It's actually writing completely new code. So, and the idea is that it's actually supposed to vectorize very well and it's supposed to parallelize very well on these many integrated force architectures. And so it's constantly work in progress. So it's constantly changing. So just a few things to keep in mind. So the problem we have is at LHC. So mainly we actually developing it for CMS detector, but it has much more wide applications. So the problem is that in several years, by 2022, we're going to have what we call a high luminosity LHC, which means that you're going to have more collisions happening in a detector. So the more collisions you're going to have in a detector, the bigger mess you're going to have. And from that mess, you have to find the interesting tracks. So inside the detector, we have a big magnetic field. So we have the charged particles will go through that field and they bend. If you look at the detector, you can think of a cylinder and cylinder, so multiple layers, and the tracks deflect in about 10 to 12 silicon detector layers. Again, there are some collisions that are not interesting. So again, we're trying to find the interesting bits for us. And again, so in several years, we're going to have a problem that the mess is going to be much more bigger. And that's basically computational intensive. So we can get up to 10,000 hits per layer. And again, as I said, this is a very intensive computational task to try to figure out what kind of tracks are interesting and from this particular mess. But all the events we record in the detector are independent. So we use like a picture, which you can process independently. And same applies for the tracks. So each track can be computed independently. So this basically means the very embarrassing the parallel system. You can take tracks, you can take events and process them one by one. So if you're actually interested more into this, we have a few papers. And basically, we want to stick with the Kalman filter. So Kalman filter was de facto the best parallel approach, which we have for many years. So we want to stick with that, basically. So the way you do the tracking is that you start from a small seed, a few layers. So it's what you call a seed tracklet. And then you propagate to the next layer. So you take that seed, you propagate to the next layer, you figure out what are compatible hits, and then you do propagation, and you pick, for example, there's a naive implementation, you pick the best one, or you pick for that particular seed tracklet, you pick, for example, the 3 best ones. And then you propagate to the next layer, and again, you pick the 3 best ones for that particular initial track. And so we have very small structures. So here is this 60 megabytes, and the track is 240 megabytes. And again, we have a very embarrassing parallel system. So the problem is we don't have a big matrices, but you have a lot of small ones. So 3 by 3, 6 by 6, and we do a very standard matrix operations, and we need to feed that. So if you want to work on multiple tracks, we need to feed those matrices into vector units. So Mateusz wrote a thing called the matriplex. So another way you can think of it as a matrix major storage of particularly just to feed the vector units. So initially it was done, so there's a Perl script which actually you can tell that I'm going to be operating on a matrices 3 by 3 or 6 by 6, and it's going to generate a C++ or Syntrix code to actually work with these kind of matrices. This was done initially because the Intel compiler couldn't do it very efficiently, but that's more or less is gone. So compiler does a very good job. And we also know that some of elements of these matrices can be 0, 1. Yeah. So initially we used an OpenMP, but as you can see, we had some problems with the load balancing. So we moved to TBB, so TBB dynamic task queuing and ability to steal the tasks allows us actually better balance the work across the systems. It does look like the TBB actually has a higher ramp-up time, but overall it's actually better for balancing your work. So if you look at the parallelization of this thing, we're going to quickly see that up to, so for Xeon up to physical cores, we scale very well. Same applies for KNC, up to 60 something, we actually scale very well. And you want to look at the red one, the red line. And also, we just run the same code on KNL, so there's no optimization for KNL, and we can see that actually we have completely worse parallelization speed up on the KNL. But if you look at this one, so our 24-thread Xeon Sandy Bridge actually still is the winner. And we just barely finally have a KNC matching it. So the biggest problem we have is that we have to constantly switch between the vector format and back to the object format. Because again, the problem is that you have a vector and you pick the 3 best track candidates per that initial seed. That means the rest you can dump. So it's constantly changing. So you have to go back and forth. And this is a very inefficient. And another big problem is we have is L1 cache. So if you look at our problems, you barely fit it at L1 cache. So this is why you probably see that on the KNC, it scales very well up to the physical cores, and afterwards, actually, you start losing. If you look at vectorization for the fitting, so fitting actually looks very good. So if you move from 256 bits to 512 bits vectors, you more or less almost get twice more performance for the fitting in vectorization. For finding is more complicated. It's constantly shifting. Yeah, so we have tons of problems here. Still have tons of things to understand. We have different results with different ICC versions. Again, we're working with Intel. We're feeding what was wrong, so that's constantly changing. We have a hard time to figure out how to use vector units usage reports. And also, our kernels are extremely small, so trying to figure out what's happening with L1 and L2 caches are very problematic. We know that if we do manual prefetching, we can get about 10% or something. But again, if you overdo, you lose the performance. If you look in the track findings, and we look at the speed up, again, this is a matter plus vector width. So again, when you generate, you can say, oh, we're going to have a 512-bit vector size for matriplex. So it's not, so we still do it like up to what the hardware allows. And then you can see that for Xeon and KNC, we get the speed up to over 2, and we get better vectorization speed up on KNL. But if you look what's happening in reality, you find that the KNL is actually extremely slower if you run in a scalar mode. So basically, you ask matriplex to generate a code which is scalar, so one single element. Instead of actually using a long vector, it's actually a lot slower. Yeah, so that's basically it. So we are looking into various things. So we care about memory accesses, prefetching caches, sizes, bandwidths, latencies, trying to figure out how to use the vectorization reports, how to use creatively TBB, how to deal with those very small objects we have in the memory, how to constantly reshuffle the data efficiently. And that's more or less it. And I think in the last 3 days, most of these questions have been answered. We saw a lot of presentations of KNL, and we saw today presentations of our VTune and how to look into particular memory objects and locations. So I think most of it's already answered.
A minute and a half, if anybody has any questions. No? Okay, I have one. So you said that you need to go through your list and basically pick only those elements that satisfy some condition and like pack them down. So have you looked into using the vcompress instructions from AVX512 at all?
Probably not. Okay.
Okay, all right. So let's thank our speaker.
Okay, thanks. Okay, hi. My name is JD Emberson. I'm a postdoc here at the ALCF. I work as part of the Theta Early Science program, for which I work on the code HACC. So I want to talk a little bit about some of our early experiences with HACC on the KNL. So what is HACC? HACC is a cosmological structure formation simulation, which in a nutshell means that it basically evolves a set of n-body point particles from an early time in the universe's history to later times, generally around the present epoch. And HACC was built with the design philosophy in mind that it would be easily portable and highly customizable to different system architectures, hence the name HACC, which actually stands for Hardware Accelerated Cosmology Code. So the underlying calculation in HACC is the gravitational force. So gravity is a pairwise force between points of particles. So the brute force method of calculating gravitational force would be to sum over all pairs of particles in the simulation. Such an operation would scale like n squared. And with state-of-the-art cosmological simulations now pushing to the trillion particle scale, such an operation would obviously be extremely prohibitive. So such simulations instead make use of much more efficient ways of calculating gravitational forces. For HACC, this is a two-stage approach, where the first thing we do is we lay down a particle mesh, whereby each MPI rank then interpolates the mass of its local particles onto its local mesh, and then the gravitational Poisson equation is solved on the global mesh using MPI parallelized Fourier transforms. The second thing that we do is we append to this long-range gravitational force a short-range gravitational force interaction. And the specific details of how this is done actually depend on the architecture that we're using. So for example, on a GPU, what we do is we use a direct sum over the pairwise forces of individual particles, so direct PP interaction. And this calculation is offloaded onto the GPU itself. On non-accelerated systems or CPUs such as the KNL, we instead use a tree method, which I'll talk a little bit more about on the next slide. And so as you might imagine, the bulk of our computational time is actually spent in the short-range force calculation. And this is a good thing because when we go to optimize on a different machine, we know exactly where we need to focus our efforts. And also, in general, it's relatively straightforward to optimize because the short-range force calculation is a local quantity only relying on nearby particles, and therefore doesn't require MPI communications with neighboring ranks, et cetera. So on the KNL, for example, the tree structure works in the following way. On a given MPI rank, we divide the volume into a set of chaining mesh cells of width cm. And then inside each one of these chaining mesh cells, we build an independent RCB tree. And the depth of the tree is determined by a parameter called ppn, such that once a given leaf node has less than ppn particles on it, the tree bisection stops. Okay, so this means that we don't actually build the tree all the way down to the single particle level. And the utility of having this flexibility and being able to adjust the tree depths by changing cm and ppn is that the code is highly flexible and can be, we can pick those parameters to optimize whatever particular system we're working on. And I'll also quickly note that while we're building the tree itself, we take care to make sure that our particle arrays are properly aligned and also sorted so that when we pass the interaction list to the actual PP force kernel, the entire calculation can be vectorized, which is very important on KNL, for example. And also, we parallelize the tree walk itself by using dynamic scheduling of OPENMP threads. Because of Newton's third law, you have to be careful here to avoid race conditions in such a case. With the previous version of HACC, what we would do to prevent race conditions is we would assign a thread lock to each individual tree, so one per chaining mesh cell. We found that on the KNL, this was somewhat problematic, simply because we have a lot of cores on the KNL, and therefore, in general, have a lot of OPENMP threads doing the parallelization. And so we found quite a bit of thread contention, particularly in the early stages of the simulation when particles were more or less homogeneously distributed and the PP force kernel wasn't being hammered that much. So we recently implemented more of a fine-grained thread locking mechanism where we assign a thread lock to each individual leaf node. And so we found that on the KNL, this drastically reduced thread contention and was just an important step for us. So when optimizing the short-range tree calculation, there are basically two things that we need to do. So the first thing we need to do is optimize the actual PPE force kernel itself. So this is work that was done by Vitaly Morozov, who talked in good detail about this during one of Monday's tutorial sessions. What we found in our test is that if we compare the optimized KNL kernel to the optimized VGQ kernel, we find about 6x speedup on the KNL compared to the VGQ. And this is in the ballpark of what we'd expect just from comparing various specs of the two processors. So for example, the KNL, we have 4 times more vector usage. The wall clock time is slightly smaller on the KNL, but we can do twice as many floating point instructions per cycle on the KNL. So if you multiply these 3 numbers, you get 6.4, which is around what we're finding, which is reassuring. And then the second thing that we need to do in our tree optimization is empirically determine the optimal values of CM and PPN. So what's nice about the KNL is that the fact that we have this highly efficient kernel, which is for the most part due to vectorization, the KNL is favoring smaller values of CM and larger values of PPM compared to the BGQ. So what that means is the KNL favors more shallow trees with fatter leaf nodes, which just means that it's disfavoring the complex tree build and actually favoring the n-squared PP interactions. Okay, and then I'm going to finish with just a couple of scaling results. So last month we had early access to Theta here at Argonne. So we decided to do a couple of scaling tests. So this first test was a strong scaling test where we held the problem side roughly fixed. So we had 2048 cube particles, and we changed the number of nodes that we threw at it, going from 64 to 2048 nodes, and slightly changing the geometry a bit for 3072 nodes just to fit the geometry of the simulation. And so the different points are data points. The lower set of curves are for the FFT calculation, which is part of the particle mesh calculation I talked about earlier. And the top set of points is the overall time step. And the solid yellow lines are ideal strong scaling. And so you can see that we follow roughly ideal strong scaling up to 3072 KNL nodes. I'll also quickly note that these tests were done using 8 ranks per node and 16 threads. More careful tests on single node systems have found that our sweet spot is around 8 ranks and 8 threads. The reason why we have a small amount of ranks is simply due to the fact that in HACC we buffer around each MPI domain. And if you just increase the number of MPI ranks, you actually increase the surface area to volume ratio of your individual domains. And that leads to a computational overhead. These tests were also run in cache quad mode. We've also tried in flat quad mode, and we haven't found much of a difference between cache and flat. Okay, and then this plot is now just a weak scaling test where we held the number of particles and the volume on a node fix and just increased the number of nodes. And so again, we find roughly ideal weak scaling on theta. Okay, so just to summarize, we found 6x speed up in the optimized KNL short-range force kernel compared to the optimized BGQ kernel. Because we have this highly optimized kernel, we've now been able to remove workload away from the complex tree build and put it into the kernel itself. Our preliminary tests on single node KNL systems have found that our sweet spot is around 8 ranks per node and 8 threads. We don't find much dependence on flat versus cache, and we exhibit ideal strong weak scaling up to 3072 nodes. Thank you. The tree is built every time step, yes.
So could you introduce some way to reuse that tree built in some redundancy of the particles that go?
The problem is that if the particles move a lot, then you just have to simply rebuild it. So I don't know of any good way to be able to do that, unfortunately.